There is a stretch of the Goldfields Highway outside Leonora in Western Australia where the landscape looks like most of the northern goldfields. Saltbush, red dust, a roadhouse, a two-lane tarmac ribbon emptying into scrubland. Ordinary, arid, unremarkable. Except past the tree line, hidden from the road, sits an open pit over 90 meters deep where haul trucks move around the clock and where physical gold is being mined at one of the highest grades of any active operation on the continent. That is not the strange part. This pit is not new. Prospectors pulled gold out of this exact patch of earth in 1897, decades before anyone built a paved road through the region. They pulled it out again in the 1930s, during 2 world wars, in the 1980s, and now again in an operation using satellite mapping and cyanide-free processing. Most people driving past have no idea that history is under their tyres. Ask most Australians to name a gold mining region, and they say Kalgoorlie, the Pilbara, or Bendigo. Almost nobody says the quiet scrub outside Leonora. How did one of the oldest documented gold deposits in Australia end up treated as an afterthought? And why, after a century of being opened, abandoned and forgotten, is it producing more gold right now than at almost any point in its history? What people used to assume about this landscape was straightforward, that the dry expanse of the Yilgarn Craton had surrendered its shallow secrets to 19th century rushes, and whatever remained was too deep or low grade to justify industrial scale. That assumption was reasonable in its time. Early prospectors relied on surface outcrops, dry blowing and hand-sunk shafts hitting bedrock at 30 meters. When quartz veins pinched out, the official record logged the site as exhausted. But the first crack in that narrative appeared deep in the ancient basement. Gold was first documented here in 1897, when prospector Benjamin Hale found flecks of gold in alluvial gravel along a dry watercourse, then found gold-bearing ore beneath it. Within a decade, he built a 10-stamp battery, and the Sons of Gwalia deposit was born. For a while, the operation barely survived. Surface gold ran out by the early 1900s. Deeper ore, locked inside tough greenstone and sulfide rock, proved difficult to process because no one on site could crack the metallurgical puzzle. During the mid-20th century, the mine took on a second life supplying bullion for the wartime economy. In 1942, military requisitions and labor shortages forced operations to stall, leaving equipment to rust in the red dust. By any measure, the mine should have ended there as a half-built operation sitting on stubborn ore. It did not end because, in the late 19th century, the owners had hired a German mining engineer named Adolf Thiess. Brought in because existing processes left most gold in the tailings, Thiess developed a chlorination and fine grinding process recovering up to 90% of gold from refractory sulfide ore. Production exploded. By the turn of the century, the site ran a multi-stamp battery processing over 100 tons of ore a day, becoming one of the most productive operations outside Kalgoorlie. In 1908, a high-pressure boiler exploded, killing workers and destroying the primary crushing circuit. The mine limped along before closing in 1912. It returned briefly during both World Wars and again in the late 1980s, opening, producing and closing like something that refused to stay buried. What historical operators failed to understand was the underlying geology. Western Australia's gold exists because of a vast greenstone belt within the Yilgarn Craton's Kalgoorlie terrain. Over 2.6 billion years ago, long before Australia took shape, this rock formed part of submarine volcanic island arcs in an Archaean ocean. Underwater hydrothermal vents discharged mineral-rich fluids into oceanic crust for millions of years. Gold settled into layers of volcanic basalt, sediment, and iron formations. Tectonic collisions squeezed these volcanic sequences, folding them into greenstone belts welded into the continental nucleus and buried under hundreds of meters of cover. The gold at this site arrived from an Archaean seafloor across a vanished ocean, sitting quietly under saltbush and acacia scrub. For most of the 20th century, nobody looked deep enough. The gold price was fixed, the deposit was deemed complex, and large-scale sulfide processing tech did not exist. That changed in 2007 when an exploration entity acquired the tenements and began the decade-long environmental and heritage permitting process required to reopen the site. In 2015, an Australian-listed resource company, working alongside geological consultants and Geoscience Australia datasets, acquired the project. In 2017, the open pit operation reopened for the 5th time as a modern complex targeting over 100,000 ounces of gold annually. Diamond drilling beneath the pit keeps turning up ore older survey methods missed. Regulators are reviewing proposals to expand the footprint by 400 hectares and extend underground decline operations. Economic analysis places the mine's annual contribution to the WA economy at over $700 million, supporting close to 2,000 jobs, with projected 10-year impacts past $9 billion. None of that shows from the highway. You see a roadhouse, a church, saltbush, red dust, and nothing resembling billions of dollars. Western Australia's mining framework operates under a state-managed lease system where surface pastoral leases and subsurface tenements remain distinct under Crown ownership. What makes this site strange is an entire regional identity that stopped talking about its foundational gold strikes. Victoria built mythology around Ballarat. Kalgoorlie built fame around the Golden Mile. This stretch of the northern goldfields let its story fade until most Australians forgot it happened here. The gold hid behind a narrative that other regions told louder. That gap between local history and regional identity is closing. Drill cores pulled from beneath the open pit add to resource estimates that keep climbing rather than shrinking. Engineers are finding gold-bearing ore in quartz carbonate stockworks below depths 19th century batteries or 1980s equipment could reach, proving the deposit's true size was never fully mapped. The expansion under review would extend the footprint by 400 hectares and open deeper underground workings. If approved, the mine operating in 5 years will look nothing like the one that reopened in 2017 or the one Adolf Thies refitted in 1900. Gold and critical mineral exploration across ancient cratonic margins has become a national priority again, right as the only regional deposit that never stopped producing keeps finding more. This pit is one working node on a geological belt extending across hundreds of kilometers of the Yilgarn Craton, a belt early analysts wrote off before deep diamond drilling existed. That has always been the pattern here. Benjamin Hale was just a prospector working a dry creek bed in 1897. Adolf Thies arrived, refined a chemical extraction process, and transformed the site overnight. Geologists who walked away mid-century were not wrong about the rock. They simply lacked the geochemical models and drilling tech to reach what lay below. The gold in this ground has survived economic crashes, a boiler explosion, 2 world wars, and a century of being abandoned. It remains there today, pulled out at higher volumes than at almost any point since 1897. The scrubland outside Leonora was never a household name or tourist highlight, but beneath the saltbush and red soil, something that arrived on volcanic islands 2.5 billion years ago sits exactly where it has always been. To understand why this pit keeps yielding gold, one must look far past colonial prospectors, sheep stations, and state survey lines. The origin of this anomaly belongs to an epoch before the Australian continent existed. For tens of thousands of years, traditional owners, including the Wongatha people, lived on and managed this country, maintaining an intimate physical and cultural connection long before European cartographers arrived. What was thin was never human presence, but the official record, the written survey sheet, the geological bulletin, the assay. The deep geological story begins roughly 2.7 billion years ago, during the Neo-Archaean era, when the Yilgarn Craton underwent tectonic assembly. Volcanic belts vented hydrothermal fluids enriched with gold, iron, and sulfur into deep-sea sediments. Squeezed by colliding continents, extreme heat and pressure folded the rock into greenstone belts, trapping gold within quartz veins and sulfide structures kilometers down. Over 2 billion years, while mountain ranges eroded globally, the Yilgarn Craton remained a rigid anchor of ancient crust. Then came millions of years of subaerial weathering. Spared the scraping action of major continental ice sheets, surface rocks sat exposed to intense chemical weathering under warm climates. This created a thick regolith, a blanket of oxidized rock and ferruginous duracrust reaching depths of 50 to 100 meters. Water percolating through this zone dissolved and redeposited minerals, concentrating fine gold near the surface in alluvial channels while masking unweathered sulfide bodies beneath. When prospectors arrived in the late 19th century, their understanding of geology was shaped entirely by surface expressions. In 1897, miners mapped outcropping quartz reefs and nuggets in dry creek beds. Early mining took place in this shallow, oxidized layer. For a decade, hand tool extraction and stamp batteries yielded strong profits, but beneath 50 meters, oxidized rock gave way to hard greenstone packed with iron sulfides. Surface gold was easy, but deeper gold was chemically locked inside pyrite and arsenopyrite lattices. By 1905, traditional amalgamation using mercury extracted only 40% of the gold in unweathered ore, sending 60% into tailings dumps. Operators assumed the field was failing, misreading a metallurgical obstacle as a physical limit of mineralization. Only when fine regrinding and chemical leaching were applied was the true depth recognized. Even then, operations were constrained by steam power and manual drills. Geological Survey of Western Australia records from the 1920s show that while geologists suspected mineralized structures continued downward, capital and tech to reach them were out of reach. reach. For decades, published state maps marked the boundary of the Geologcal domain as a finite, shallow belt bounded by barren granites. Archives recorded what had been extracted, but left open what was missed due to cover, deep regolith, and structural complexity. This incomplete picture led mid-20th century syndicates to abandon shafts, believing the field exhausted. But as modern exploration developed, geophysicists using airborne magnetics and deep seismic profiling looked beneath the regolith blanket. What they found overturned 80 years of survey history. Localized gold veins worked by 19th century miners were not isolated pockets, but minor offshoots of a continuous shear zone extending hundreds of meters into Archaean crust. The mineralization core had never been exhausted, it had simply been invisible to surface surveys. Yet, with this deep framework mapped, modern resource companies face a new question. If gold extends thousands of meters below the desert floor, why did it take until the 21st century to prove the deepest zones held the richest grades? The shift to scientific certainty happened because the way geologists evaluated the subsurface changed completely. For decades, exploration relied on surface mapping and hand-drawn mine plans. Miners traced quartz veins poking through red soil, blind to what lay beneath 50 meters of regolith. The break came when modern techniques allowed scientists to see straight through solid earth. The first breakthrough occurred when the Geological Survey of Western Australia, alongside CSIRO teams, compiled aeromagnetic and gravity survey data across the Yilgarn Craton. Flying low-altitude transects in light aircraft with magnetometers, geophysicists mapped magnetic field variations caused by magnetite and hydrothermal alterations in the greenstone belt. Where surface maps showed monotonous scrub, aeromagnetic data revealed a hidden skeleton, structural fault lines, sheared fold axes, and intrusive bodies stretching across hundreds of kilometers. Old surface workings were not random, isolated reefs. They aligned along regional shear zones where fluid migrated billions of years ago. To confirm structure geometry, exploration companies in the late 1990s and 2000s turned to seismic reflection profiling. Sound waves generated by vibrator trucks bounced off underground rock layers, recording reflection times to surface geophones and generating cross-sections down several kilometers. Seismic profiles proved ore-bearing shear zones did not terminate at old workings, but plunged steeply into basement rock for thousands of meters. Then came physical proof via deep diamond core drilling. Unlike early percussion methods pulverizing rock to dust, diamond bits retrieved intact cylinders of rock from over 1,000 meters down. When geologists sliced open core samples, evidence was indisputable. Locked inside dark metabasalt and quartz carbonate veins were fine strings of visible gold alongside iron sulfide minerals. Laboratory fire assays and mass spectrometry confirmed high gold grades in zones previous generations declared sterile. Further precision came from analytical tools. Scientists used isotope ratio mass spectrometry and uranium-lead zircon dating to establish mineralization timelines. Isolating zircon crystals in host volcanic rocks, research teams dated primary volcanism to approximately 2.7 billion years, while hydrothermal veins dated to around 2.63 billion years. This proved gold deposition occurred during a specific fluid flow event tied to regional metamorphism during Archaean assembly. Geochemical sampling of surrounding soils showed extensive halo anomalies extending far beyond immediate quartz veins. Satellite imagery and LiDAR were layered over subsurface datasets, allowing geologists to line up surface topography with historical cadastral maps and mine workings. Digitized into three-dimensional modeling software, historical shafts lined up along newly identified mineralized trends. Old prospectors had only scratched the top edge of a continuous geological engine. Modern instruments proved the initial model of a depleted surface field was wrong. But knowing gold is down there raises a practical dilemma. How do you extract millions of tons of deeply buried rock in an arid environment without repeating past environmental and economic failures? Today, the reality of this Archaean anomaly is expressed in heavy machinery and environmental engineering hidden behind the scrub line off the highway. The pit has expanded into an open-cut excavation, with terraced haul roads winding down past 90 meters depth. Yet, because the landscape is flat, dominated by low mulga woodland and saltbush plains within the Shire of Leonora, passing drivers see almost none of it. The operation remains visually invisible from the main road, marked only by security signage and occasional dust plumes. Underneath, the economic footprint is vast. Independent regional analysis estimates the operation's total annual contribution to the WA economy at over $700 million. Breaking down that figure, $250 million goes to direct operational expenditure, $80 million covers royalties to the state government, and $40 million funds local wages for roughly 800 site personnel alongside contractor roles across the northern goldfields. The projected $9 billion 10-year impact relies on market estimates, but confirmed figures demonstrate how a single shear zone underpins a regional economy. That economic drive comes with environmental management challenges in an arid ecosystem. Operating a processing plant in a region averaging under 240 millimeters of rainfall annually requires water management precision. Deep underground operations intercept hypersaline groundwater aquifers. To prevent salt contamination of surface soils and ephemeral creek systems, the company runs dewatering and desalination circuits. Saline groundwater is pumped out, treated for carbon-in-leach plant use, or redirected to evaporation storage facilities under Department of Water and Environmental Regulation oversight. Tailings management remains a critical responsibility. Fine rock powder left over after chemical leaching contains trace processing agents and must be stored in tailings storage facilities engineered to withstand rare storm events driven by tropical depressions. State inspectors monitor these embankments for stability and seepage. Furthermore, because the site overlaps with country where First Nations Australians hold long-standing cultural authority, modern operations require consultation with traditional owners, including the Wongatha people. Native title agreements, heritage surveys, and rehabilitation frameworks ensure culturally sensitive sites are protected before expansion occurs. The proposal to expand the operation's footprint by 400 hectares and extend underground decline workings beneath the pit represents a shift in how deep Archaean deposits are worked. Rather than relying on surface expansion alone, miners trace ore vectors down decline tunnels, plunging hundreds of meters into greenstone bedrock. This minimizes surface disturbance while doubling access to high-grade ore. As modern engineering proves, century-old mines can be brought back at scale. A larger question remains. What does this tell us about the rest of the continent, where hundreds of historical goldfields sit quiet under sand and scrub? The deposit outside Leonora is not an isolated tale of a lucky prospector or an unusual patch of ground. It is the story of how an entire continent's geological history was misread because 19th century tools evaluated only what was visible at the surface. What kept this mineral system unrecognized for so long was not a conspiracy or an omission from map sheets, but a fundamental geological assumption. Early surveyors assumed that when surface veins pinched out at shallow depths, the geological engine that created them had reached its end. What actually kept the magnitude of this deposit hidden was a structural misinterpretation. The belief that the deeply weathered regolith of the Yilgarn Craton marked the bottom of the ore system rather than temporary cover masking a continuous Archaean shear zone. For a century, official survey maps treated shallow workings as finite, localized features. It took airborne geophysics, seismic reflection, and deep diamond core drilling carried out by Geoscience Australia, CSIRO, and commercial exploration entities to reveal surface veins were merely the upper edge of a multi-kilometer crustal structure. Yet despite modern data, questions remain unresolved. Exploration geologists are actively drilling to determine how far south and west mineralized fluid pathways extend beneath hundreds of meters of cover. While core samples confirm high-grade ore past 1,200 meters depth, precise structural boundaries of the lower shear zone remain estimated rather than fully mapped. Furthermore, across the goldfields, hundreds of historical surface workings logged in state archives during the early 20th century sit untouched under regolith cover, their true subsurface extent unknown to modern science. The official map sheet always looks complete when published in a ledger. The lines are crisp, boundaries drawn, and labels suggest everything of significance has been catalogued. But the ground beneath pays no attention to human cartography. The Archaean rocks outside Leonora sat quietly through 2 billion years of continental assembly, weather, and surface change, indifferent to whether surface occupants called the site exhausted or operating. Which place in your own state or territory has always struck you as having a hidden history buried just beneath an ordinary landscape? Let us know in the comments below, and if you want to explore more forgotten geography and deep historical